Hello, Assalamualaikum. We are from Group 9 and today we will present about our topic early stage diabetes risk prediction dataset. So now let's dive into why we initiated this project. In the healthcare sector, decision support system or DSS are vital tools that help practitioners make better decisions by leveraging raw data. By integrating machine learning, we can significantly improve prediction accuracy for early disease detection. For our project, we chose the J48 decision tree algorithm because of its simplicity and clarity, making it easy for medical staff to understand and use. Using Weka, an open source machine learning tool, we've developed a prototype that predicts diabetes risk based on patient symptoms, allowing for quick, informed clinical decisions. To ensure a structured development process, we applied the Herbert-Simon decision-making model. So this model provides a clear roadmap for solving complex problems through four distinct phases. The intelligent phase, where we identify the problem, the design phase, where we build the solution, the choice phase, where we evaluate our options, and finally, the implementation phase, where the system is put into practice. In the intelligence phase, our primary focus was problem identification and data collection. We identified a pressing need for early diabetes detection to prevent complications. So we utilized the early stage diabetes risk prediction dataset, analyzing key symptoms like polyuria, polydipsia, age, and gender. So before moving to the model development, we pre-processed this data to ensure it was clean and ready for analysis. Moving on to the design phase. So we focused on building the diagnostic model as shown in the Weka interface on the slide. We selected the J48 algorithm. During this stage, we further cleaned the dataset to remove errors or missing values. By identifying the most significant symptoms, we were able to create structured decision tree branches that form the logical backbone of our diagnostic tool. In the choice phase, we evaluated our model to ensure it was the best possible solution. We used tenfold cross-validation to guarantee that our predictions were reliable and not biased. By analyzing performance metrics, specifically accuracy, precision, and recall, we confirmed that the J48 model was the ideal choice. It offers the perfect balance, providing high predictive accuracy while remaining a transparent, easy to understand tool for medical professionals.
So I will continue with the implementation phase. So in this final phase, we integrate the selected J45 decision tree model into a fully working decision support system. Through the system interface, users are able to enter patient symptom data such as age, gender, polyuria, and polydipsia. Based on the input provided, the system automatically generates an immediate diabetes risk prediction, which is classified either positive or negative. So the effectiveness of this system is monitored through prediction result and user feedback to ensure that the system produces accurate and reliable outcome. So this implementation phase complete the Herbert-Simon decision-making cycle by transforming the analytical decision model into a practical tools that support early diabetic risk management and data-driven decision analysis and design. In this phase, we analyze the several decision support system techniques, including decision tree, flowchart, the analytical hierarchy process, and production rules to identify the most suitable approach for early diabetic risk prediction. The early stage risk prediction dataset was consist of 520 patient record was selected for this project. So to enable machine learning analysis, the dataset was converted into ARFF format for use in Weka. The dataset include demographic attributes such as age and gender, as well as key clinical symptoms including polyuria and polydipsia. Each patient record is classified as either positive or negative. So in this phase, Weka was used to build J48 decision tree model, while Draw.io was used to design supportive diagrams such as flowchart and HP model. So this ensure that the decision making process is structured and easy to come to the decision tree. So in this project, we are used the J48 decision tree algorithm implement in Weka to develop a diabetic risk prediction model. The model was built using the 520 patient intents from the early stage diabetic risk prediction dataset. So the generated decision tree produce clear and understandable classification rules, allowing the decision-making process to be easily to interpret. So the final model consists of 22 leaf nodes with an overall tree size of 43, providing a structured and transformed decision model that is suitable for early stage diabetic risk prediction. The J48 decision tree used for diabetes risk prediction, including the model description and its visualized structure. So from the decision tree visualization, as you can see, polyuria is identified as the root nodes, indicating that it is the most important predictor in the model. So the tree then branch into other symptoms such as polydipsia, irritability, gender, age, alopecia, and delayed healing. So forming a step-by-step decision path. Each branch represents a clear if-then rules that leads to a final classification. So a strong positive classification is observed when both polyuria and polydipsia are present, covering 193 patient intents in a single leaf node. So overall, the model achieved an accuracy of 95.96% and provide a clear and transparent decision-making structure, making it suitable for early diabetic risk detection in a healthcare decision support system. The decision table and evaluation result of J48 point decision tree model. The model was evaluated using 10-fold cross validation on 520 patient intents to ensure reliable and unbiased performance. So the results show that the model correctly classified 95.96%, which is 499 cases, while 4.04% or 25 cases were misclassified. So the kappa value of 0.9156 indicate a strong agreement between the predicted result and the actual outcome. In addition, the error rates are low, with a mean absolute error of 0.0549 and a root mean squared error of 0.1975, showing that the model performed accurately. The final decision tree contains 22 leaf nodes with a tree size of 43, highlighting polyuria and polydipsia as the key indicator for early diabetes risk classification.
The classification model used in this experiment is the decision table, trained on 520 instances from the full dataset. The model generated 136 decision rules, and any unmatched instances were classified using the majority class. So the feature selection was performed using a forward search approach where 139 subsets were evaluated, and the best achieved a merit value of 68.077, indicating strong performance. So the final model selected 11 relevant attributes, which is and was evaluated using leave one out cross validation. With a training time of only 0.09 seconds, the decision table model proved uh, to be both efficient and effective for this classification task. So we move to the flowchart. This flowchart illustrates the step-by-step decision-making process used to classify diabetes rates based on several key attributes, including polyuria, polydipsia, itching, delay healing, gender, and age. The process begins by evaluating whether polyuria is present and continues through a series of clear decision points based on symptoms and demographic features. At each stage, the model checks specific conditions and directs the classification toward either positive or negative derivatives risk outcome. So by following a structure rule-based flow, the flowchart demonstrates how different combinations of attributes lead to accurate and interpretable classification result. So an influence diagram is used to show the relationship between attributes in the early stage derivative risk prediction dataset. So it visually represents how variables, decision, and outcomes are related using nodes and direct arrows, helping to clarify dependencies in the decision-making process. The influence diagram illustrates the central class node connected to system clinical and demographic attributes, including age, gender, polyuria, polydipsia, sudden weight loss, weakness, polyphagia, genital thrush, visual blurring, itching, irritability, delay healing, partial paresis, muscle stiffness, alopecia, and obesity. So this structure highlights how each attribute directly influence the final diabetes risk classification, making the relationship between variable clear and easy to interpret.
Okay, next, this slide show the influence diagram. From the diagram, we can see that each clinical attribute directly depend on the class variable. Means the class node represent the diabetes risk result and other attribute in the model. In the total, the network include 16 attribute. Some of the key attribute are age, gender, polyuria, polydipsia, sudden weight loss, and weakness. These factors are placed under the influence of the class node, showing their pattern. Have the system decide whether a person is at positive or negative risk of diabetes. This structure allows the bias network to calculate probabilities based on how these attributes behave in real data. By learning from training data, the model can estimate how likely a person is to belong to each risk category. And in conclusion, the influence diagram help us clearly to see the relationship between the class variable and all clinical attribute. Show the diabetes risk classification is strongly cut by multiple symptom and patient characteristic working together. Okay, for analytical hierarchy process or AHP, uh, the main goal of this model to decide whether a person has a positive and negative risk of diabetes. At the top of hierarchy is our goal, determine diabetes risk classification. We use several important criteria, and the criteria are taken from the J48 decision tree, help us to identify the most factor related to diabetes. And among all the criteria, polyuria and polydipsia are the most important. These two symptoms are strong indicator of diabetes. They are supported by two additional factors, which is gender and age. At the top of hierarchy are alternative, which are the final outcome, positive risk or negative risk, by compare all the criteria using the AHP method. The system calculate the weight and combine them to make the final decision. In conclusion, AHP help Our system make a structure and fair decision by considering the importance of each factor. This allow the system classify diabetes risk more accurate and support better health decision. Okay, for production rule, generally using the part classify in Weka, the part algorithm combine decision tree learning with rule-based classification to produce clear and easy to understand if-then rule. These rules are used to classify a patient in two categories, positive or negative diabetes. For example, a rule say if polyuria is yes and polydipsia is yes, then the patient classified as positive risk. This made the model very transparent and easy to interpret. In the total, the model produced 15 rules to make sure the results are reliable. Was evaluated using tenfold cross-validation, means the data was split into 10 parts and the model was trained and test multiply time using different combination, and the result shows strong performance. The model achieved 96.92 accurate, correctly classified 504 out of 520 case. Also have high kappa value of 0.9351, which mean the agreement between predict and actual result is very strong. In additional, the error value are low with MAE of 0.0361 and RMSE of 0.1711. This low error indicate that the model made very small prediction mistake. Okay, in conclusion, the production rule are clear, accurate, and reliable. Help doctor of all system user easily understand how the system make decision about diabetes. Okay, that's it for diagram. Next, we move to result to see what the outcome of the system.
So now for summary performance. To validate our model, we apply the decision table algorithm to a dataset of 520 patients using tenfold cross-validation to ensure statistical stability. The results were exceptional. We achieved 96.15% accuracy rate, correctly identifying 500 out of 520 cases, with kappa statistic of 0.9178. The model shows a near perfect agreement with actually clinical diagnosis. Finally, our low error matrix, specifically an MAE of 0.23, confirm that the system is not only accurate but highly precise in its probability. Now, for class-based performance evaluation, our model show exceptional reliability for both risk group. For the positive class, we achieve a recall of 0.988, meaning we capture nearly every at-risk patient. In the negative class, a precision of 0.979 ensures that healthy individuals are rarely misclassified. Overall, the weight F measure of 0.961 and RAN NMCC of 0.919, which you can see in the summary table, prove that the system is highly effective at discriminating between these two critical groups with very high confidence. To visualize the model precision, we look at the confusion matrix for all 520 patient instances. The decision table algorithm correctly identified 316 positive cases and 184 negative cases. Most importantly, we saw a very low error rate
of only 3.85%. Out of 520 tests, there were only 4 false negative, which is critical for patient safety in early diabetes screening. This result confirmed that this decision support system is both reliable and highly accurate tool for clinical risk assessment. So in conclusion, our project demonstrates a decision support system that prioritizes transparency without ignoring accuracy. By using J48 and PAR algorithm, we create a model where the decision-making logic is fully visible to the user. Our use of tenfold cross-validation ensure that system is both stable and reliable for high-state environments. Ultimately, this DSS serves as a powerful tool for early identification, ensuring that data-driven insight lead directly to timely life-saving medical intervention. That's all from us. Thank you.